Engineering Dynamics, uh, Session 5, Kinematics of a particle. Let's solve more problems in kinematics of a particle. So in this example number 4, we have a bicycle moves along a straight line or road, and its position described by the graph shown below. We want to construct the velocity versus time and acceleration versus time graph for time period of 0 to 30 seconds. So to solve this problem, for first part, for velocity time graph from displacement time, which is given and has two sections. So section 1 uh, provides with a equation of displacement of t squared time squared, and the second part is a straight line which is defined by displacement is equal to 20 times t minus 100. So as we know, velocity is derivation of displacement over time. For the first part of our graph, which is from 0 to 10 seconds, s is equal to t squared, and its unit is feet. So v, we know velocity is derivation of displacement over time, so it just goes for 2 times t. And for the other part, from 10 to 30 seconds, s is equal to 20 t minus 100, so the derivation of this part is just 20 feet per second. As soon as we have the two-part velocity, we can easily draw velocity versus time, which is a slope line for the first time with a slope of 2 times of t, and a constant line for the second part from 10 seconds to 30 seconds by the numeric value of 20 feet per second. That's the construction of velocity versus time graph. Now let's go to acceleration versus time graph. So acceleration is derivation of a velocity over time. For the first part, velocity is 2 feet, so acceleration is going 2t, 2 times t, so derivation of that is 2, a constant number of 2 feet per square seconds. And for the first part, v is a constant number, so derivation of it is going to be 0. If you draw acceleration versus time, it's going to be 2, a constant line for the first part, and 0 because the velocity is constant for the rest of the time period. Let's attempt another example. So in example number 4, the car provided in the figure starts at the rest and travels along a straight track such that it accelerates, and this graph is provided 10 meter per square second for the first 10 seconds, and then decelerate by a negative 2 meter per square seconds. We want to draw the velocity versus time. We have acceleration versus time, and we want to draw velocity versus time and displacement versus time, and also determine the t prime, the time, which is here, needed to stop the car. Also, we want to know how far has the car traveled when it goes to a stop. So let's see how we can approach our problem. First part is velocity time graph. We do know dv is a times dt for initial condition because it starts at rest at t equal to 0, velocity is equal to 0. For time between 0 to 10 seconds, a is 10 meter per square seconds, and if you draw the velocity, it just come by a graph of velocity versus time. So let's see how we can draw it. Integration of dv from 0 to v is an integration of 0 to 10 a dt, and a is 10. Mm. So v is equal to 10 times t from 0 to 10. So it says at t equal to 10 seconds, velocity is 100 meter per second, like what we have draw here. Mhm. And v is equal to 10t, Mhm. like the equation we get for it. Mhm. And also using 100 meter per second as the initial condition for the starting point of the second part, starting for the second part time period, it just gives us a integration from 100 meter per second to velocity to an unknown velocity. dv is equal to 10 seconds to t minus 2t dt. That's a for the second part, decelerate by this amount. That's a dt. And velocity from 0 to v, velocity from 100 to v for the second part is equal to negative 2 times t from 10 seconds to a t or t prime. Will equalize t with t prime. So it just gives us an equation which says v minus 100 is a negative 2 times in parentheses times minus 10 seconds, and it just gives us an equation for velocity for second part, and that's a negative 2 times a time mhm, plus 120. Mhm. That's how we can construct v velocity versus time from from acceleration and time. So when t is equal to t prime, we have v equal to 0 because it just comes to rest. We want the time when it comes back to rest. So in that case, if you set this equation to equal to 0, it just gives us t prime is equal to 60 seconds. We can solve this part from a more direct solution, and that is delta V is equal to 0, and delta V is area under acceleration. So if you add up these two areas with each other, A1 plus A2 goes 0 because the car goes to rest to go to 0. It goes stop, so delta V finally goes 0. So A1 plus A2 should be 0, and they are the area under acceleration time graph. So that says 10 meter per square seconds times, and this time period based off problem statement is 10 seconds. 10 meter per square second times 10 second plus a negative 2 meter per square second plus this time t prime minus 10, because this is 10, t prime minus 10 for the second part goes 0. It just directly gives us t prime is equal to 60 seconds without any integration, just by the area under graph. And also for displacement time graph, we have provided with acceleration time graph. We just draw velocity versus time graph, and ds is equal to v dt, again based off initial condition of problem statement. At t equal to 0, it was at rest, start at rest, v is equal to 0. So based on that, from t between 0 to 10 seconds, v is equal to 10t. We have it here. And if you integrate it 0 to s ds, integration of 0 to s ds is equal to integration of 0 to t vt. So that's 10t dt. And that gives us a displacement is a function of 5 times t squared. So at t equal to 10 seconds, s is equal to 510 squared, and that's 500 meters. And if you just do the displacement time for the second part, so it just gives us a v is equal to negative 2. Let's say this is 10 to 60. V is equal to, yes, that should be 10. That's because for this is for the first part. This is a my negative 2t plus 120 meter per second, and 500 meter is going to be the displacement at the starting point for the first part, the second part, and to s ds is integration of 10 second to t and v dt. If you do the math, it just gives you s minus 500, and 500 we just calculated in the previous slide for the end of the first period. So s minus 500 is equal to a negative t squared plus 120 t minus in bracket 1 uh, in bracket negative 10 squared plus 120 times 10 close bracket. And if you do the math, it just gives you this equation for displacement. And if you draw the displacement versus time is going to have the same equation which we just derived. Mhm. Based on meters. So S is equal to this equation, and when T prime is equal to 60 seconds, S is equal, you can replace uh, T prime for 60 seconds in displacement equation to get a displacement of 3000 meters. That's displacement at the very end. That's how far car travels before it stops. You can also solve the second part based off a simpler approach, and that's a more direct solution again. And that's more direct solution is the triangular area under VT, always the area under velocity is displacement. Area under velocity is displacement. So delta S is equal to S minus 0 from 0 to 60 seconds, because displacement here is 0, and we want to know what is the total displacement. That's the area under these two triangles. So if you add them up together, it just says one large uh, uh, one large triangle with a height of 60 and height of 100 and length of 60, which is t prime is equal to 60 seconds. That delta S gives you direct a 3000 meter. That's displacement 3000 meter. Thank you. We'll review the projectile motion and move to kinetic of motion in next video. Thank you.